Hello students, we shall now discuss some topics on numerical analysis, particularly on the interpolation. You know that in interpolation, which means, what does it mean in interpolation? In mathematics, interpolation means to estimate the value of a function. Say the function is fx for some particular value of the independent variable x on the basis of the value of the function at the surrounding values. Suppose we are given with a table like this. Please see the table. Table is given for some different values of x's and the corresponding values of yi, which are fxi. You notice that the given xi's are not all equi-spaced. It is 1.1, 1.3, then 1.7. These are all, these x's are called the arguments or the nodal points of the table. What we require now is to estimate the value of the function y is equal to fx at some given point of x, beginning with at x is equal to 2.0. That is a value which is not given in the table. We first note that in the above table, xi's are not equally spaced, but quite often we shall find that xi's are equally spaced, so that xi's are equal to x0 plus I into h, where h is the step size. Usually h is taken to be very small in magnitude. Now we further assume that fx is continuous in the region from x is equal to a, x0 is equal to a to x is equal to b, and we are interested only within this region, and we don't have any idea about the function beyond that region. The analytical form of the function fx is either known to us or it may not be known to us, and there may be situations when the function fx, the analytical form of the function fx, is quite critical in nature, which are not amicable to any mathematical methods such as for differentiation, integration, etc. In either case, we shall try to replace the given function fx by a simpler one, say by phi x, which can be easily handled and can be amicable to any mathematical formulation. When phi x is a polynomial in x, the process of replacing fx by phi x is called polynomial interpolation. When the data series shows some sort of, say, periodicity, then we seek for trigonometrical series for phi x. The process is then called trigonometric interpolation. Similarly, we may have exponential interpolation function for f phi x. You know that the simplest possible form of a function is the polynomial function, and that is why we are concentrating our objective on the polynomial interpolation. What is a polynomial? You know that phi x is a polynomial taken in this form, where a0, ai, etc. are the real numbers called the coefficients of the terms. It is of nth degree, and we assume that an is not equal to 0. Sometimes we favor for shifted power series. Shifted power series is of the form phi x is equal to a0 plus a1 into x minus c, something like that, as written in the, where c is some point situated in the interval of tolerance. Now, what is the basis that such a function, any given function like phi x, can be replaced by a polynomial? Yes, we have some justification against this assumption. It is due to the Weierstrass in 1885, which states that every function which is continuous in an interval ab can be represented in that interval to any desired degree of accuracy by a suitably chosen polynomial, and that is to say, given epsilon, very small number, pre-assigned small positive number, it is possible to find a polynomial, say phi x, such that mod of phi x minus fx, that is the absolute difference, is absolute value of the difference, is less than epsilon at every point of x in the interval ab. It can be represented geometrically as follows. See the curves. Here we have the curve, say this is the curve for y is equal to fx, this is the curve is y is equal to fx. We draw two lines two curves. So this the lower one is y is equal to fx minus epsilon, the upper one is fx plus epsilon, and see the curve which is in the broken line, it is y is equal to phi x. This is the polynomial curve representing the curve original function y is equal to fx. Also observe that at some points phi x and fx coincides. For example, if this is the point at x0, phi x is equal to fx, at x1 also phi x is equal to x1, and x2 also fx is equal to phi x2. These are the nodal points. So at any other point varying this x0, x1, x2, xn, at any other points phi x differ from fx very small. The difference is very small. So we can replace the given curve fx by means of the polynomial curve phi x at all points within the limit a to b. This theorem is the basis of the polynomial interpolation. The problem of polynomial interpolation. Let us given with the values y0, y1, y2, yn with the values of the function y is equal to fx corresponding to the values of the arguments x0, x1 up to xn. So note that x0s are all different and there is no two values y0s which are equal to each other. This is our primary assumptions, and x0, x1, xn is something in order, so that xi is equal to xi plus h. We assume that fx is continuous in the interval and the value of yi's are approximately are accurate to the rounding of errors only. It should be remembered that the analytical form of fx is either not known or very complicated in the form. This is so that we have to estimate the value of y is equal to fx at any point of x in the region a to b on the basis of the given data set xi, yi. Weierstrass theorem assures us that we can find a polynomial phi x as close as to the given curve representing y is equal to phi x in AB. We seek for such a polynomial which is close to fx, and at the nodal points x is equal to xi, phi x coincide with the fx. Now this is the conditions by which we would like to determine the polynomial function fx. Let phi x be a polynomial which is given by x0 plus a1x plus a2x square, something like that, am x to the power m. Am is not equal to 0, so that the polynomial is of degree m with real coefficients a0, a1, am. These are the m plus 1 parameters which are to be determined with the help of the n plus 1 conditions of phi x as given by the equation 1. We thus have a linear system of n plus 1 equations in m plus 1 unknowns a0 to am. Now question arises whether m is greater than or equal to m or less than m. There may be three possibilities. Let me discuss these possibilities. First of all, let me assume that n is less than m. That is, the degree of the polynomial is higher than the number of nodal points. That is, we are facing a situation where there are more unknowns but less equations. There will be infinite number of solutions. In fact, there are m minus n number of parameters which can be chosen arbitrarily. For example, let us consider 2 points x0 and y0, and we try to fit in it two curves, a curve of degree greater than or equal to 2. Then you can see that there may be an infinite number of curves like this. So there is no unique polynomial of degree 2 or more passing through the data points. The next case where n is greater than m, that is, there are more equations but less number of unknowns. Obviously, in such cases there is no solution for a0, a1, mn, and hence there is no polynomial like phi x of degree m which is less than n with a0, a1, mn as the coefficients passing through all the data points. What we can do now? However, we may assign arbitrary set of values to a0, a1 to am, then supporting points, that is x0, x1, xn, the calculated polynomial value will certainly differ from the given values of the x, y0, y1, yn. Such differences are called residuals. Finding AIs in a way to minimize the components of residuals leads to a different solution of the approximation of function, including least square approximation or min-max polynomial approximation, etc. Now, the situation when n is equal to m, this is the very important situation, that is, there are n plus 1 interpolating equations, independent equations with equal number of unknown. In that case, there exists a unique solution for a0, a1, am, that is a0, a1, an, because am is equal to n, and we get a unique solution for phi x of degree m, that is degree n, that would pass through each of the given n plus 1 data point. This is the case of polynomial interpolation. It may be noted that in this data value are correct up to our accuracy level. However, with failed data level, when yi's, maybe xi's also, are not so accurate, then use of interpolation does not make any meaningful result. Let me explain this point. Sometimes yi can be determined from the functional form of the y, so that yi contains only the rounding of errors. But there are many situations, particularly in the social sciences, when yi are taken from the market research. In that case, yi are not so accurate as compared to the accuracies in x's. In that case, there is no need of finding a polynomial curve which is passing through each of these data points. That is a separate question, and we shall opt for the least square method or something other method for approximation of functions. Now, let us consider the polynomial determination with equi-spaced nodal points. We consider the case when n is equal to m and there exists unique polynomial phi x of degree n which interprets the data set, that is phi xi is equal to fxi, where I varies from 0 to n is finite. We take xi's to be equi-spaced, that is xi is equal to x0 plus I into h, I varies from 0 to n and h is greater than 0 is the step size. Xi's are called the argument or the nodal points or nodes. We first define some operation which are which are of many importance in finding the linear functional space when the nodes are equi-spaced. These operations will be required in our further calculation. Let us first consider what is shift operator. Shift operator is denoted by capital E and is defined like this. If the given data point, if the given data set be x is equal to x0, x1, x2 up to xn, corresponding y is equal to y0, y1, yn, where xi's are equi-spaced, that is xi is equal to x0 plus ih, then y1 is equal to fx1 is equal to fx0 plus h, because x1 is x0 plus h, it is called E of fx0. That is, E means the shift operator operated on fx0 resulting fx1, that is y1. Similarly, we can say that y2 is equal to E of fx1, something like that. The operation is defined in this way. This is the shift operator, and in general, E square, we define E square, that is E of E, double operation, which result in fx plus 2h. So note that E2, that is, we may call it is its square, is give us to fx plus twice h. Similarly, E cube gives us fx plus k into x plus 3h, while e to the power k, that is k is a real positive constant, will give us fx plus k into h. Thus, E2 of fx0 is y2, E3 of y0 is y3, etc. Now, there is something different meaning, that e to the power minus 1. We may call it inverse operator. E to the power minus 1 of fx is fx minus h. And similarly, e to the power minus k is fx minus kh. And in general, if ekfx is, note that e to the power kfx is not efx whole to the power k. Don't do this one. Now let us come to the second operator, which is very important, is difference operator. Difference operator, we use this symbol delta to define the difference operator as delta is equal to fx is equal to fx plus h minus fx. It is called the first order forward difference. Now similarly, forward difference operator delta is defined as delta of fx is equal to fx plus h minus fx. It is called the first order forward difference. Similarly, we can write delta of y0 is y1 minus y0. Delta operated on y1 will give us y2 minus y1. Delta operated on yn minus 1 give us yn minus 1. The second order difference means delta square of fx, that is delta on delta fx, that is delta operated on fx plus h minus fx, which gives us this result. Delta square fx is fx plus 2h minus 2fx plus h plus fx. That is, following this above rule, we can write delta square on y0 will give us y2 minus 2y1 plus y0. Similarly, delta square on y1 give us y3 minus 2y2 minus plus y1, etc. Similarly, we may have higher order finite differences. For example, delta 3y0. Delta 3y0 gives us y3 minus 3y2 plus 3y1 minus y0. Note that the coefficients 1 minus 3 plus 3 minus 1. Similarly, delta ry0 is delta 5y0, say delta 5y0 is y5 minus 5c1 y4 plus 5c2 y3 minus 5c3 y4 y2 plus 5c4 y1 minus y0, and in general we can write delta k on fx is equal to given by this formula. This formula can similarly be obtained from the above result by way of mathematical induction. So please remember this formula while using the delta operator, that is forward shift operator. We now consider another difference operator which is known as backward difference operator. The backward difference operator, which is represented by this symbol as shown in the paper, is defined as delta on operated on fx plus h give rise to fx plus h minus fx. So that if we operate delta on y1, then we will get y1 minus y0. If delta operated on y2, we will get y2 minus y1, etc. Similarly, we can go for higher order backward difference operator as follows. Delta square, or sometimes we may call delta 2 on yi give rise to yi minus 2 yi minus 1 plus yi minus 2. This should be keep in mind that in general delta of order k operated on yi give us to summation k r is equal to 0 to k minus 1 whole to the power r k cr into f of x minus r into h, where k lies between 1 to n. So this is the backward difference operator. Now we go for central difference operator represented by delta. Central difference operator is defined as delta operated on fx will give us fx plus h by 2 minus fx minus h by 2. Similarly, higher order central difference operator can be defined as delta nth order delta, that is delta n fx give us to delta n fx is equal to summation k is equal to 0 to n minus 1 whole to the power k n c k into f of x plus n by 2 minus k, that into h. This is operator central difference operator delta. Now we consider the averaging operator or mean value operator mu. Mu operated on fx give us the average of fx plus h by 2 and fx minus h by 2, that is half of fx plus h by 2 plus fx minus h by 2. This is the averaging operator. So we consider, we have just discussed about some of the operators right from the shift operator e then forward operator delta, backward operator delta, then averaging operator mu, and central difference operator delta. There are interrelationship between these operations.